so the goal now is to show that if the gamma delta n's converge almost surely to gamma, then gamma has to be an SLE6. So step 2 is to show that almost surely if KT denotes the envelope, I mean, it's not exactly the envelope, or actually the filling of gamma up to time t, then it satisfies the property 2. Right? Or I didn't remember if it's 1, 2, or AB, but the second one that we had at the beginning. So we want to prove, one, that it is possible. Remember, gamma was defined in the metric that we used. We see that gamma and gamma prime are basically, if you have two continuous curves that are just two reparameterization of the same curve, in our metric, they are distant 0 from each other. So the curves here are defined modular time reparameterization. So here, when I say that A of KT is T, just means that it is possible to find, it is possible to reparameterize so little a. It is possible to reparameterize gamma T in such a way that A of KT is equal to 2 times T. So when can you reparameterize a continuous curve in such a way that this A of KT is equal to 2 times T? Well, just need to prove, so we just need to prove that T gives A of KT is almost surely increasing, right? Well, the fact that it converges to, goes to infinity when T goes to infinity will come for free. So you have to prove that A of KT is continuously increasing. It never stays constant, it always increases. And once you have this, then you can choose the time parameterization in such a way that A of KT is equal to 2 times T, and still with this time parameterization, gamma will remain continuous. Okay? So this is the first thing that we need to check. And the second thing, once we have this, will be the local growth condition. But the local growth condition will come for free, right? Once we have A, the local growth condition comes for free. Why? Because, first of all, you know that gamma is uniformly continuous, is almost surely uniformly continuous with respect to time in 0, t0. So that means that because you know the curve is, you have reparameterized the curve in such a way, you have chosen a given parameterization, and then for this parameterization, the curve is continuous. So it's uniformly continuous on a finite, on a compact interval. And if you know that it is uniformly continuous on the finite interval, then you know that for any epsilon positive, there exists delta, such that for any t smaller than t0, the diameter of gamma between t0 or t and t plus epsilon smaller than delta. No, sorry, t plus delta smaller than epsilon. Okay, that's what it means to be uniformly continuous. And we know, and by definition, gamma t plus epsilon t plus delta disconnects k t plus delta minus kt in h minus kt. So what I'm saying is, if you know that your curve kt is defined by a compact set, by a curve gamma t, then even when basically, say, k is going to swallow something big, anyway, it is created itself by gamma. And so gamma between t and t plus delta has a small diameter, and that's all you need in order to disconnect what happens here from the outside. So if you have a Loewner chain, kt, I mean, you don't know yet it's a Loewner chain. If you have an increasing family, and you have a continuous curve, and you define the envelope of this curve, then the local growth condition will come for free as soon as you have this condition here. So what we need is to prove A. So in this step 2, we need to prove A. That t gives A of kt is continuously increasing. So there are two statements here. The first one is that it's continuous, and the second one is that it's strictly increasing. You know, it doesn't remain constant on intervals, so when you reparameterize it, gamma remains a continuous curve. So remember, kt is the filling of the continuous curve gamma up to time t, right? So it's gamma union the inside. So the fact that A of kt is continuous, of course, by definition, A of kt is non-decreasing, right? It cannot become smaller with time because k is growing. Right, and because gamma is continuous, right, between t and little t plus epsilon, you just add a little small piece, you know, to k. I mean, you add a little piece. So what comes for free, the fact that gamma is continuous, implies that A of kt is continuous. This is a very simple, maybe I don't spend time with that. This is a simple exercise. You know, if you add a little something here, then the half-plane capacity can only, cannot have a big jump. So what we need, the difficult part, I mean the non-trivial part, is that T give A of kt is non-decreasing. So in other words, it never remains constant. It always strictly increases. So what we want to say is that for any t smaller than t prime, almost surely, A of kt is strictly smaller than A of kt prime. So because A is, anyway, we know that A is, so now I'm getting confused with non-increasing. And so in English, increasing means strictly increasing, right? So, sorry, so increasing. So, well, that's what we want to prove. Okay? And because we know it's non-decreasing anyway, it is enough to prove it for, in fact, it's enough to show that for any two rational numbers, q and q prime, almost surely A of kq smaller than A of kq prime. Right? For any two given times, it's sufficient to prove that A of KQ is more strictly than A of KQ. So if we have this, because we know it's continuous, then we are fine. We can choose a time parameterization in such a way that the thing grows according to half-plane capacity. We know it satisfies the local growth condition for free, so it will be a Loewner chain, and therefore there's a function W behind. No, I mean the parameter. Yes, I mean the parameterization is. Yeah, I mean we want it. If we want to define something which is a Loewner chain, the time has to be 2 times t in order to define W. So you know, any strictly continuous. I mean, any continuously random increasing function, you can always reparameterize it in such a way that increases linearly. The important thing is how the shapes. You know, here it's not the time parameterization that matters; it's the shapes. So, okay. So, here's a lemma, which is important because this is going to be used on several occasions, including in the coming lectures. So remember, gamma delta n converges. So remember, so we define sigma for any z in the upper half plane. You define, let me write it this way, but this is just sigma delta n, which is just tz delta n, if you want. This is the disconnection time of z by gamma delta n. So what I mean here is I take a point z here, I have gamma delta n, and here I have A. Right? You have the discrete exploration process. The first time, so it's the first time at which gamma delta n disconnects, oh, I forgot something, z from A in d delta, and we take deltas here. And define sigma z, which is t of z, is the first time same at which gamma up to time t disconnects z from A. Right? So you have two possible ways to do this. The first one, in both cases, I mean, the first possible way to disconnect z from A would be, for instance, by doing this. You know, at that moment, you have disconnected it, and the other option would be that gamma, you know, makes a circle around something like that. If one of these two things happens, then this is the time at which that you call sigma of z or sigma delta n of z if you are in the discretized version. Now, of course, when I define this, so this is not yet the lemma, right? So I'm just putting down some notation. When you define this, there's a little remark that you have to say is, what time parameterization do we use here? So what we use here is we are not yet allowed to use the time parameterization by capacity. Okay. So here, when I say sigma and sigma, I say the first time t such that, it's where the time parameterization what we use. is that, so it is one time parameterization of gamma up to time, of gamma, defined as a space on the space, your favorite possible time parameterization of gamma that you can use given the fact that you are tightness and there exists a holder or whatever parameterization, and that of the gamma delta n's is the one that makes that the infimum, or the supremum of gamma of t minus gamma delta n of t goes to 0 as n when t. Right? We know the distance between this and this goes almost surely to 0. That means that there is a time parameterization that makes it possible to stick them together. So we take a continuous time parameterization of gamma, which we can choose, and it's not very difficult to show that even though gamma is random, there's a natural way to choose one. And then we just choose the time parameterization that sticks to this one for the discrete approximation that remains closed. Now the lemma is that gamma delta n, that sigma, so for each fixed z, sigma z delta n converges almost surely to sigma z. That means in the discrete case, I have the gamma delta n's that will disconnect gamma at disconnect z at a given time. So you have the path of up to this disconnection time of discrete disconnection time, and you have the path up to the continuous disconnection time. The claim is that these two guys, the path up to the discrete disconnection time converges to the path up to the continuous disconnection time. So what could go wrong? So of course, you know, what we know is that there's an easy thing, which is that the lim inf of the sigma delta n z is larger than, is smaller than sigma z almost surely. Right? Why is that? It's because imagine that all the discrete curves disconnect here. Well, then in the limit, because gamma delta n's converges to gamma, if all the gamma delta n's disconnect at a given time, then the limiting guy also disconnects. Right? So when you have a discrete disconnection guy, if it's already disconnected in the discrete setting, you pass through the limit, then the continuous guy also disconnects at that point. Okay? So this is easy. So what could go wrong, and what can go wrong is the other way around. So there are two possible ways. The first one is basically, I mean, the idea is that the discrete guys, you know, they come close to disconnect, but they don't disconnect. So that the actual disconnection time is larger, and that still this close to disconnection thing narrow down when n goes to infinity, and that the discrete guy, even though the discrete guys don't disconnect at a given time, the continuous guy will do it. So for instance, if you have gamma delta n, which is, so it doesn't disconnect here, so it's z is here. So this is gamma delta n. And when n goes to infinity, these things become closer and closer, but don't disconnect, right? So then what you would get is that then the limit of the sigma delta n's, right, could be much larger than sigma z. Could happen, you know, that the discrete curves don't disconnect, but that in the limit they touch. So how do you get rid of this? So the idea is fairly simple, and it's easier to explain on a picture than to write down the formal statement. So basically take epsilon small. Suppose gamma delta n comes epsilon close to disconnect z at the given time. So you wait for the first time at which, if you make a ball around gamma delta n at a given time t, z is here, that if you add this ball here of radius epsilon, that then sigma is disconnected from infinity. Z is disconnected from infinity. So you take the discrete curve, yeah, and you stop at the moment where it's close to disconnect. You know, it's almost so, and this is the type of thing that will happen anyway in these configurations. Right? This type of thing would happen for each epsilon in the bad configurations where the discrete guy, you know, narrow down but don't actually disconnect. So stop there, and then now look at the conditional probability that once you stop there, what is the probability that you actually do not disconnect z immediately after that time? Well, you know, the discrete guy, and this is going to be a statement that is uniform with respect to delta. I arrive here, I know that I'm at distance epsilon of disconnecting. Now, the discrete exploration, remember, it's this thing that discovers sites of different colors. So what you see here is that here you have a green, say. Here you have red on the other side. And here you have Z. So because Z is fixed, maybe there's one little remark that one can do. Z is fixed, so by Russo-Seymour-Welsh, you know that around Z, with very high probability, there will be, you know, a green circuit and a red circuit. If you allow the circuit to be small, then, you know, given Z will be almost surely protected, you know, and therefore the curve gamma will not be, you know, will not go through Z. It will be at positive distance from Z. So it's away from the curve gamma. Now, when you arrive here, what you know, so that you can draw here, you have the ball of radius epsilon, and here you have maybe a ball of radius larger, which is, say, delta, such that Z is still a distance, is still not in that ball. So this is not Z. Z is here and here, gamma t, sorry. Okay. So when you are, the t is almost this disconnection time, and you stop at that moment, then what you see is that you still have plenty of sites that you haven't explored. In particular, what you know is that because of Russo-Seymour-Welsh, if epsilon is small, with very high probability, you will have a green circuit here and a red circuit in this annulus of size between annulus of radius epsilon, between radius epsilon and capital delta here. Now, if you have these two annuli here, these two circuits in the remaining thing that are not explored, in particular here, for instance, in that picture, what you see is that, you draw it like this. In particular here, you will have a green crossing from here to here. And you have a red crossing from here to here. Okay. So that means that gamma delta, the discrete guy, so this happens with a very large probability. When the smaller epsilon, the larger the probability is that you see this picture at that almost disconnection time. And if this happened at the almost disconnection time, that means that gamma, it is blocked on one side by this red thing and on the other side by the green one, because it has to go through the two things. And so gamma will actually have to disconnect Z soon after this almost disconnection time. Okay? So this little argument, you stop at an almost disconnection time, and then you just use Russo-Seymour-Welsh, and the fact that you choose this is true for each given z, this will tell you basically that when I am at an almost disconnection time, and I let the epsilon go to 0, then I will, in the limit, when epsilon goes to 0, the limit of the almost disconnection times will be, with probability 1, the disconnection time in the discrete case. I mean, uniformly in the discrete case. So this argument exactly, so this argument, so I didn't write it down formally, I just wrote down the picture because I guess it's simpler to understand it this way. This argument shows that indeed sigma z delta n converge to sigma z. So this is true for, of course, you see this is true for z fixed. It's not true simultaneously for all z's. Because there might be, points that the discrete guy hits, or that, so it's for each fixed z, you remain at, you know that you are with high probability the curves pass at positive distance away from z, and so you know that such a capital delta here exists, and then you can apply this little argument at almost disconnection times versus true disconnection time. Okay. So why am I doing this? Because there are different ways to justify. You see here in that picture, this way is sort of almost trivial. Yeah? You have the feeling that once you are almost disconnecting, you disconnect really in the discrete case, because in a way that's a part of the argument that can become nasty if you don't use this approach. So, for instance, in the paper by Kamiya and Newman, when they proved this convergence to SLE6 by a different method, the analog of this part is actually nasty because you have to do some uniform estimates using 5 arms and so all sorts of tricks, which is doable, but this part is substantially simpler here. So what you see here is that the discrete disconnection time converges to the continuous guides. Okay. So now we want to prove, remember what we are after. We want that T gives A of KT to prove, want to prove is almost surely increasing. That's what we are after. So again, we have to look at the different scenario that would prevent this from being increasing. So the first remark is the following, and this is actually the place where we use the fact that the boundary of D was a continuous curve. It's not really needed, but so you have your domain D is like this, right? So we fix, remember we fix Q. Okay, so we have gamma up to time Q here. So gamma itself is a continuous curve. Right? So it is not very difficult to see that the boundary created by a continuous curve, so that the boundary of KT, the boundary of D minus KT is a continuous curve. This is just a simple topological fact that, if you take the boundary of a continuous curve, then it's a continuous curve. Some little, and so we are looking at so gamma is doing something like this, and so that's the domain we are looking at, right? So the boundary of this thing is a continuous curve. Now, the first remark is the following, is that you can take a dense, countable dense subset of this boundary. Right? Because it's a continuous curve, you just take one parameterization of these things and take the image of the rational points on this boundary. So you take a dense countable subset of this curve. So you have a dense, so maybe I don't go into the details, but this notion of dense is with respect to seen from the inside, so it's important, it's easier to, I don't want to discuss what a prime end is here and these type of things, but if you have a boundary as a continuous curve, then dense is with respect to this parameterization of this continuous curve. You know, maybe you could have, you know, you have little issues like, you know, if the boundary is like this, a point here corresponds to one boundary point on one side, one boundary point on the other side, and they have to be counted twice. So when I say dense, I mean is each side of the boundary is counted once. So you see the boundary as a continuous curve, and you follow the continuous curve. So you take a countable subset of this curve. So let's call in this uj, these. And now, because of Russo-Seymour-Welsh, almost surely, for each j, uj is surrounded, is protected in d minus kt. In the discrete case, okay, should be. Let me put it this way. For any j, gamma does not hit uj after time q. So I have this countable dense set of boundary points. And I ask the question, does gamma, after time q, you know, I choose one, does gamma go through exactly this point here with positive probability? The answer is no, because in the discrete case, in the discrete approximation, you know, this guy will be, you can find many concentric annuli here around this point xn, and in each of these guys you have a positive probability that to be protected by you know, a semi-circuit that prevents the curve gamma of entering this semi-annuli. So therefore, because of this argument, what you see is that the discrete guys, for each given point here, the discrete gamma delta n's will not be allowed to enter this with high probability, and eventually they will have to, you know, go around because there will be a circuit in the discrete percolation picture. And because the gamma delta n's converge almost surely to the gamma, this will actually prevent gamma itself of hitting uj. Maybe this is a bit sloppy. I mean, you see here there are many, many arguments that you have to go through. So I know that I could give more details here, but on the other hand, you know that if I give more details each time, then it would become too long, and then you would lose the track of the argument. So here you have this little argument that tells you that because you took it to be a countable set of points on the boundary, and you know that each given guy is not hit by the curve in the later on, that means that almost surely this is true simultaneously for all of them, right? Because you took a countable set here. So that means that the curve gamma, you know, it has to avoid all these given boundary points. And gamma is a continuous curve that doesn't remain constant, right? So this argument tells you that gamma between q and q prime does not sneak, let's put it this way, I don't know if this is an English word, I think so, along the boundary of KT union boundary of D. So what I mean is that there exists, almost surely, there exists S between Q and Q prime, such that gamma S does not belong to the boundary of D union boundary of KT. You know, gamma is not constant, right? It's a time parameterized in such a way that it's always increasing. So what I'm saying here, that the curve gamma cannot, you know, go along the boundary of the domain here. That's forbidden, because otherwise it would have to hit all these, I mean, several of these points that we just showed they are not hit. You have a countable dense subset so on the boundary, so you cannot travel along the boundary. You have to avoid these points and remain continuous. So you know you don't sneak along the boundary. So you have two options for gamma. So two options. So either there exists S such that gamma S is in the interior of D minus KT. So that means that here you have gamma Q, and sometime later gamma, you know, is here before times Q prime. Okay? So if you are in this case, then you are happy, because that means that necessarily the capacity of has increased, because and then it is okay. A of K Q prime is strictly larger than A of KQ. The capacity has increased because you have penetrated a little bit inside the domain that you still have to explore. So this is fine. Then the second option which is a problematic one, is that, okay, we know, so if we are not in this case, we know that gamma has to go somewhere. So we know already it doesn't go along the boundary here. Okay? We know it, and we guess it doesn't go here in the inside of the remaining domain. So where does it have to go? If you doesn't forbid here, then it means that it has to go somewhere here in the inside. It has to go somewhere here. Right? So if this is not true, that means that there exists S in Q prime such that gamma S is disconnected from, so remember we go to A by gamma up to time Q. Right? So that it's somewhere in the part that has been already erased. So, but here this means exactly, maybe I should just draw the picture. In such a case, it means that the discrete guy, that you have gone into the inside of your hull. That you have gone, to visit a given point here, which is in the inside there. And so this said that basically here, there's this moment where you decide to go inside or respect to outside, and at this is a disconnection time. And at this disconnection time, you decide to go, in the continuous disconnection time, you decide to go to inwards. Now, the discrete disconnection time is the limit of the continuous disconnection time is the limit of the discrete disconnection times. And at the discrete disconnection time, by definition of the discrete exploration process, the discrete exploration process, when it does what it does disconnect here, it is forced to go outside, because by definition you go outside. You aim always at A, right? You follow this interface. When you disconnect, then you have to bounce to the direction where you want to go. So you know that because of this lemma, that discrete disconnection is the limit. I mean, the continuous disconnection time is the limit of discrete disconnection time. You know that this second option almost surely doesn't hold. So you see here, there's a. I did it on purpose, slightly presented in a slightly intuitive hand-waving way, but that's the way you prove these things. You have to be careful, and one has to be aware of the fact that in each of these type of arguments, when you say, well, we see that, it has to go inside, outside, one has to be very careful, because it's very easy to make a wrong statement about, things about curves that topologically go to the right or go to the left, and this cannot happen, this cannot happen. But here, you can be safe and make all this rigorous, right? So what we said here is the following, right? If I fixed Q, gamma Q, if I fix Q, immediately between Q and Q prime, the curve gamma cannot sneak on the boundary. It can also not enter into into the hull of KT, because that would say that there was a disconnection time before, such that you have entered, the remote past, and this cannot happen because the discrete disconnection time converges to the continuous guys. So the conclusion is that necessarily between Q and Q prime, at some point you are somewhere, have entered, the domain, in the real inside of the domain that you have still to explore, and that in that case the capacity seed from A of this guy increases strictly between Q and Q prime. Because this is true for any rational Q and Q prime. This will tell you that the capacity of gamma up to time t is an increasing function, strictly increasing function of time. Okay. So therefore, conclusion of all this, one can reparameterize the continuous function gamma in such a way that A of kt is 2 times t. Because it's a strictly increasing function, we can choose the parameterization to be the one that gives capacity t, or 2 times t to the curve of 2 times t. Now, there's a little remark that you can make here. Remark. If we parameterize also gamma delta n by its capacity. Remember, gamma delta is a continuous, you can view it as a continuous curve, that you draw on this given lattice, on the hexagonal thing. And actually, this continuous curve, gamma delta n, that you draw on the hexagonal lattice, this one is truly self-avoiding, right? It never passes exactly, it may be, get to distance little delta of its remote path, but it never actually touches it. So this one, for each given delta, is a self-avoiding, is a simple curve on the lattice. So you can view it as a continuous simple curve, and therefore it's always possible to parameterize it by its capacity. So if we, so A of gamma delta n up to time t to be equal to 2 times t, then gamma delta n converges to gamma when this gamma t goes to 0 when n goes to infinity. So you know that the gammas, so what I'm just saying is that the gamma, so we are here in a bounded domain D, and the gamma delta n converges to gamma. Right? Suppose that we choose the time parameterization first of gamma delta n such that this convergence takes place almost surely for this time parameterization? Well, because they remain, gamma delta n remains very close to gamma, that means that the half-plane capacity of gamma delta n up to time t and of gamma up to time t remain very close. And therefore that the parameterization of, by half-plane capacity of gamma delta n and the parameterization of gamma delta n that you use to remain close to gamma are very close. Right? If you have two curves that remain very close to each other, then the half-plane capacities of the hulls generated by these two things are also very close. So I do it on purpose here now, you know, to explain that you have to be very careful at each step here. You know, there are plenty of things you need to take care of. So maybe now you try to say, yes?
Where did we use the
Here, no, we didn't use that it was rational. We just said that we just fixed Q and then we took once we know that it's true simultaneous for all Q. You see, we want to prove that almost surely the function T gives A of KT is strictly increasing. So one way to do it is take a dense, countable dense thing and to say that A of, that this is true almost surely for simultaneously for only Q and Q prime. So we use this here to interchange the almost surely and the fact that it's true. For each fixed Q and Q prime, this is true, and then we interchange this, and once we know it's true simultaneously for all Q prime rationals, then it's also true for by monotonicity for the real T prime. Okay, so all of this effort now since the break was to justify the following. So the following statement, which is that if gamma is a sample of a subsequential limit of the P delta n's, then almost surely KT, which is the hull of gamma up to time t, is a Loewner chain. That means what? That means that there exists a random function T gives WT. Right? Almost surely, you know, KT is a growing thing, so almost surely you can define a driving function WT that generates this KT. That generates the primary KT via Loewner's ordinary differential equation. Okay, so what time is it? I have to be. Okay, is it okay now? Do you roughly see how it goes? Remember, what we did first was use tightness, right? So again, tightness, Pierre doesn't know it, but he will make a session on tightness and what it means, you know, to wiggle back and forth and why basically the Russo-Seymour-Welsh implies that the curves, the families of interfaces are uniform, are tight in the appropriate metric that I defined. Now, once you have a subsequential limit, then you have to prove, work a little bit, but we didn't use anything but Russo-Seymour-Welsh, essentially, to say that any subsequential limit, gamma defines almost surely, almost surely a sample of a subsequential limit defines a Loewner chain. And therefore, you can define a continuous driving function WT that is behind. That's what we did so far. Now, the question is, we want to show that basically this function is a Brownian motion. Right? So that WT is a Brownian motion running at speed 6. That's now the goal. So we are slightly better off because we have defined this function W, and we know, the goal is just prove that this driving function the law of this driving function is a Brownian motion. And remember, because of what I said last time, once you start, if I would start with a Brownian motion, then this defines KT, in a deterministic way, and then it constructs the law of KT and therefore of the curve gamma. So, let us draw this picture here. So I have X, I don't remember, I think I did B here and C here, that was the picture. And remember, I chose to this exploration process to start from X and to aim at A. So gamma delta or gamma does this. Now, let us define the following event. A is the event that gamma hits. I'm going to use these two intervals here. CA before AB in the picture here. Right? So that's the event that this curve gamma, hits this thing before that one. And A delta n is the same thing with gamma delta n hits C delta, A delta before. So it's the approximate version of this one for the exploration process. Okay. Now, because of this disconnection time lemma that we had before, because of the lemma, the probability of probability of A delta n converges to the probability of A as n goes to 0, n goes to infinity, right? And in fact, if in the coupling that we had, the probability of the symmetric difference here between A and A delta n goes to 0. Because the discrete guy will hit the limit, if the discrete guy hits, if the continuous guy did hit this one before that one, then it means that the continuous ones did also. It's not possible that, the discrete guy, the continuous guys hit this one before this one, but the discrete guy didn't. That's precisely this lemma that we had before. Now, what does Smirnov's... So a remark is that A delta n, okay, it's the event that here I have X delta n, A delta n, also B, C delta n, B delta n, C delta n, right? Remember, the exploration process is this guy that separates here that has this red and so on. What does it mean that it hits this before that? It means exactly that there is a red path from here to here. Because on its right boundary, what we have found here is exactly a red crossing from here to there. Right? The probability that this exploration process hits this before this is exactly the same event as the fact that there exists a red path from here to there. Okay? Because anyway, this red path, the only way to get around suppose there's a crossing here. Right? The only way to pass, that the discrete exploration path goes through this crossing, the only way it can do it is to go this way here. To discover this guy at that point, and then because we know we have to go to B, you turn to this direction. And at that moment, you haven't hit this path yet. And when you are here, you have, on your right boundary, you have explored, you have discovered the crossing. So A delta n is a crossing event. Okay? So you know that the probability of A delta n when n goes to infinity, because of that Smirnov's result, this converges to this quantity x, right, we had at the beginning. You know what the limit is of this crossing event. You have to map these onto a triangle, and then, psi here, and then C, A, B. So A, B, X, C, and this is this distance here. No, sorry. So now, what do we have? We have, for any fixed t, look at the probability that A holds given gamma up to time t. That's what we want to understand. So there are two things that you can say. The first thing is that the probability of A delta n given gamma delta n up to time t, right? What is this? You have a small delta n, so you have explored gamma up to time. This is gamma delta n up to time t here. Here I have A, B, C, I mean they all have deltas, and X delta. Remember, I said A delta n was the probability, was this crossing event. Here at this point, you have explored this here, and this green one on the other side. So now, what is the probability still that A delta n holds? Which means that this guy hits this one before this one. This one before that one. Well, this is exactly the probability that there exists a red crossing from here to here in the remaining domain. So this probability converges almost surely to what we call xt, where xt is basically I have d gamma t. Here now I'm the continuous A BC, and I map this onto the triangle here, where this is now B, C, A, and xt is the image of gamma t. Okay? So what you do here is you apply Smirnov for each fixed t. You apply Smirnov's theorem, but now you do it not for the domain D with boundary point A, B, C, and X. You do it for the domain which is D with D minus KT, right, with boundary points A, B, gamma T, and C. Now, the claim is that in the topology I've discussed before, when I told you, well, actually Smirnov's theorem generalizes to this other topology on convergence on domains and boundary points, that for this other topology, this is true that when n goes to the infinity here in this picture, and you fix t, that this image with these boundary points 1, 2, 3, 4 here, and the domain, which is the discrete domain that is left here, that this guy converges with respect to this Kara-Teodori convergence to this domain with these 4 boundary points. You know, there might be, you know, some fjords, or I don't know. Well, actually, there aren't even fjords. But anyway, you can use Smirnov's theorem basically to prove that for each fixed t, this is an approximation because gamma delta n converges to gamma, and the endpoint converges. Everything works nicely. So for each fixed t, you can use Smirnov's theorem to say that this quantity here converges to xt, where xt is defined by mapping this domain D with gamma t, I mean D minus kt, all the way to here. So now we want to argue that this xt is nothing else than this probability that you have here. So we want to argue that this conditional probability converges to the continuous conditional probability. So of course you have to be slightly careful because here conditional probability is something which is easy to define in the discrete setting. You just have to condition on a given event. In the continuous setting, you know conditional probabilities, you have to be slightly more careful. But here there's no problem because you take, say, for instance, if you take any f, which is a sort of, say, continuous functional on the space of continuous functions, continuous bounded functional, what you end up is that the expected value of f of gamma up to time t indicate a function of a by just, you know, dominated convergence or bounded convergence, you get that this is the limit when n goes to infinity of the gamma delta n of 0t indicate a function of a delta n. So you use just this and the fact that this guy converges to this guy and that f is continuous and bounded. And so now you can apply this here to deduce, okay, I skip a line to deduce that this will be just the limit when n goes to infinity of the expected value of xt indicate a function of f of gamma delta n 0t, which is nothing else than the expected value of xt f of gamma up to time t. Right? So the conclusion is that xt is nothing else than the conditional probability of a given gamma up to time t. Right? Remember that xt is measurable, I mean, is a deterministic function of gamma up to time t. So let me now conclude this lecture to sum up what we've proved so far. The proof is not finished, but we are in pretty good shape. So remember, the goal was to prove that the discrete exploration process converges to the to something which is SLE6. What we've proved is that any subsequential limit, the thing is tight. Then we have taken any subsequential limit. We have seen any subsequential limit is a Loewner chain. Right? So there's a continuous random function W there. Now what we have here is that, so if gamma is a sample of a subsequential limit of the p deltas as delta go to 0, then it satisfies, and that's what the following property, which is that one can parameterize almost surely, one can parameterize gamma by the capacity, half-plane capacity of its hull, and it is a Loewner chain. And if one defines the event A, which is, gamma hits, CA before AB, and for any t, xt, so I have domain D here. I have gamma t, which is on the boundary of the hull that it has been created, because we said it's a Loewner chain. Then we have a conformal map phi t here, which is the conformal map that maps the remaining thing here with A, C, and B here onto A, B, and C here. Okay? And then xt is the image of this tip here. And we define this to be this distance also to be xt. No, it's the other one again. This is distance 1. So if we define all these things, these two things, and you see now they're all defined just in terms of the continuous Loewner evolution, then for any t, you get that xt is the probability of conditional probability of A given gamma up to 20. Okay, that's the statement that we have. And now you see that we are, if you forget everything up to here, the statement that I've written to the right of the blackboard is just a statement about the continuous curves. There are no discrete approximations anymore. This is a statement about the fact that if gamma is a sample of a subsequential limit, then it's a Loewner chain. I mean, it defines a Loewner chain. There is a well-defined event in terms of the continuous hitting probability. There's a well-defined quantity xt in terms of conformal maps. And then there's the statement that xt is nothing else than this conditional probability. Okay. So next time, so Thursday, we will start with the following two statements. The first statement is that this quantity here, xt, because of its definition here, is continuous with respect to t. When you increase a little bit here, this guy, cannot move, cannot jump from here to here. That's just because of the fact that kt is a Loewner chain. So this will say that xt is a continuous martingale. The path of xt is continuous, and when you let evolve t, it's like a conditional probability of a given event induced by, growing information, so it's a martingale. So we will have a continuous martingale. And so using just this, we'll be able to identify the fact that the WT that is behind the scene here is a Brownian motion running at speed 6. At speed, 6 times t. It's a Brownian motion running at speed 6 times t. So I'm aware of the fact that in some sense today was the unpleasant, the technical part of it, but you have to go through that to make this work. And also it's important to see that, to realize how many steps, you have to take care of. None of these steps is difficult. If you know what you want to do, there's no problem. At no point we did something, everything was natural. The only thing is to keep track of is what we are aiming at. What we're aiming at is just, prove that this is the scaling limit of this curve is an SLE6. In order to prove this, we have, to first say it's a Loewner chain, and then we have to identify the fact that the driving function is a Brownian motion, and in order to do this, we have to use Smirnov's theorem. Right? So that's the idea, but we have to, so one has to do it really step by step, first subsequential limits, then to make sure that it's indeed a Loewner chain, that nothing pathological happens there, then to parameterize it carefully, to be careful about this, convergence, which topology we use, and so on. But nothing is difficult. Yes?
What is the reference where we can find this proof?
Well, that's a good question. I mean, the only place where this proof is actually sort of written up in some detail, but only some detail, is the lecture notes of Park City that you have, or that are here. So the story about this proof is, okay, the proof of this statement. Basically, okay, there's the first paper by Stas, where he proves Cardy's formula. And in that paper, he promises to say, well, actually, you can prove also convergence to SLE6. And it was clear at the time that he says, and everybody, I think, agrees to believe him that I'm sure he did have a proof of the convergence to SLE6, more or less in that spirit. But he was then busy, trying to think about Ising and FK and so on. So he never wrote down actually the proof of this convergence to SLE6. And then it started to be slightly embarrassing because, okay, it was his result. He said he knows how to do it. But it was clear, to prove, say, the results on the critical exponents and so on, you needed this convergence to SLE6, and it was not there. So in particular, Kamiya and Newman, they wanted to prove things about scaling limits of families of loops that are inside this domain, and they needed it also. And so they wrote a proof of convergence to SLE6, but not along these lines. They wrote a proof along lines which I believe is more complicated technically. So I think this is a substantial simplification of the argument. And then Stas wrote, I mean, if you look at this, I think in the ICM paper, International Congress of Mathematicians, where he announces also already Ising, there are basically 2.5 pages where he just gives the outline of everything here. So, just in 2.5 pages, everything I said here is contained in there. So, of course, it's compressed pretty heavily, but on the other hand, Stas is able to say, each of the crucial steps, I mentioned, are hinted at, say this, you use that, and then it works. So this is, in a way, an expanded version of the thing that Stas outlined in that proof. Now, the situation for Ising is the following, as you will see this afternoon. There's a proof of something that resembles Cardy's formula. And, but now I think Stas will be more, part 2 will come out, where he proves convergence of the discrete Ising or FK exploration process to the corresponding SLE. He will do it himself using this type of approach. Yes?
The relation between this conditional probability and the driving function is more general than the particular case you were thinking?
You mean this?
No, because you said, okay, I'm going to now prove that this is
Yes.
Has a particular constant times
Yes.
the motion.
Yes.
You are going to start from this.
I'm going to start from this, but I'm using something very explicit, which is the fact that xt here is defined explicitly via this conformal map. So this is just specific, this statement here, you know, is specific to percolation and to the fact that the law of this guy, here you see we're using some averaging out of the percolation that still remains to be explored here by saying that this converges to this by Smirnov's result. So what we have now is, because of Smirnov's result, another way to view this is the following. Maybe I can just state it so that you understand better. If I take a very particular case, which is the particular case where the domain I'm exploring is this one. I'm starting an SLE here from point X. Here I have B, C, and A. Okay. I'm starting the exploration process from here. I get gamma T here. I define the conformal map, which is the conformal map that maps me back onto my original domain. So here I have A, B, C, right? So this is my new domain. And I take the unique conformal map such that the image of this guy inside here is back here with these three fixed boundary points. You can do it by Riemann's mapping theorem. Then the image here, you have xt, which is the image of phi t of gamma t. What we've proved is that this xt is a martingale. And the goal is to say, well, the only way such that this happens, this works, is for xt to be defined by a driving function in the Loewner equation, you know, if you map it on the upper half plane and so on, such that the wt that is behind it, the upper half plane, is a Brownian motion running at a certain speed. But you see here, we need something that satisfies a very special property. And in another domain D, it's just the conformal image, you know, of what you see here. You can map it, your domain D, onto a triangle and then adapt this. So you see here, imagine if you know that xt is a continuous martingale, then that means in some sense it's a Brownian motion in this interval with some time change, right? And what will happen is that this Brownian motion here, you know, will hit C or B first, depending if the crossing occurs in one direction or the other one. That's the idea. So then you just have to, you know, okay, we'll see Thursday morning how to conclude there. So again, this afternoon at 3, there will be the second part of easing conformal invariance. And maybe actually this will not be quite enough. Maybe I will need a third one at some point. So we'll see. But anyway, after, for those who are not interested in that, the next lecture is on Thursday morning, 9:30. And then there will be Friday morning, Monday morning, Tuesday morning, and so on. And I have to discuss with Pierre and Christophe who works when